Good afternoon. Can you hear me? I'm guessing you can all hear me. All right, perfect. Thank you again for attending the speaker session. My name is Enes Karaaslan. I'm the Connected Wises founder and CEO. Today I'll be talking about a very interesting topic about autonomous vehicles. This is a project funded by the U.S. Department of Transportation under the Small Business Innovation Research Grant. We completed the technology R&D and now in the commercialization phase. I believe this will be very interesting to you, this presentation. We can now start, I guess. Okay. Let me see if I can. I would like to first introduce our key R&D personnel in this project. I am the principal investigator. I have deep experience in AI, deep learning, intelligent transportation. I did my PhD research on similar technologies. Dr. Shen is also an expert in transportation, sustainability, multimodal systems. He has completed his PhD on electric vehicle energy optimization. Dr. Laman is an ITS expert in our team. He has quite a bit experience in the industry for transportation safety, connected infrastructure. He has also completed his PhD on similar subjects. He has done a lot of work in traffic safety optimization and simulation. Dr. Ercan is also an ITS expert in our team. He has field experience in transportation infrastructure. He has built a lot of connected infrastructure facility. Merdat is a new addition to our R&D team. He is currently an engineering professor at the Southern Methodist University. His expertise is in real-time signal processing. Bernardin is our valued developer. He is expert in Internet of Things devices, machine learning algorithms, robotic systems. We've been collaborating with the University of South Florida. Their Qatar department is assisting our project. Dr. Lee is the director of the Connected and Autonomous Transportation Systems Lab. Dr. Lin, also program director at Qatar. Dr. Medeiros is also consulting our team, helping us in the geofencing applications, vehicle route optimization. Since the audience may not be familiar with the connected automated vehicles, I would like to give a brief background about what these type of vehicles are, what this technology is about. So there is this explaining video made by the U.S. Department of Transportation. Yes, DOT has focused on CAV projects quite a bit lately. So I would like to show this short video. Maybe fast forward the majority of the parts. These CAV applications are very important component of the smart cities. and it has quite a bit benefits to our transportation safety and our traffic optimization. It will also reduce the fuel emissions by optimizing the traffic.
Imagine a future where vehicles talk to one another and to critical infrastructure. This connected vehicle technology can change our transportation system as we know it by enabling safe, interoperable, networked wireless communications among vehicles, infrastructure, and personal communications devices. Connected vehicles provide drivers with 360-degree awareness of similarly equipped vehicles within a range of approximately 300 meters. This secure system keeps personal information private and does not track your vehicle. Drivers will receive warnings that inform them of potential hazards through a visual display, seat vibration, or tone. These are only warnings. The driver remains in control of the vehicle at all times. However, the technology can also support limited automated functions in which the driver only cedes partial control of the vehicle. Warnings can help drivers respond quickly to avoid potential crashes. For example, the Intersection Movement Assist application warns drivers when it is unsafe to enter an intersection. The Do Not Pass application warns drivers when it is not safe to pass a slower moving vehicle. The Emergency Electronic Brake Light application notifies the driver when an out-of-sight vehicle several cars ahead is braking. And imagine the value of this blind spot warning application, which lets this commercial driver virtually see what's happening in his or her blind spot. Connected vehicles can communicate with smart roadside infrastructure like rail-grade crossings to alert drivers when a train is coming, even if the driver cannot see or hear the approaching train. Connected vehicles can help with weather-related traffic and safety issues too. This is especially true with conditions such as black ice, where the weather may not appear to be dangerous, but the roads are slippery. Information collected from multiple connected vehicles can help determine when a potential hazard exists, such as icy roads, and warn drivers before they experience them. Road weather data from the vehicles can be sent to Traffic Management Centers, or TMCs, providing detailed, real-time information to help monitor and manage transportation system performance. The centers can then take actions like adjusting traffic signals and speed limits, notifying maintenance crews, dispatching maintenance vehicles to the road, and broadcasting warnings for motorists. Motorists can get real-time road weather information from in-car displays by dialing 511 or by listening to highway radio stations. Motorists will be able to get road weather information on their personal devices before leaving home.
This is essentially a brief summary, especially for the safety applications. I think it's a great video that shows the connected automated vehicle technology in a very broad perspective. It essentially uses a wireless communication system. Sometimes it's cellular communication. Sometimes in different applications we've been using DSRC, dedicated short-range communication. The main objective, of course, is to now, with the increased market penetration of autonomous vehicles, we can help those vehicles in the challenging road environment by sending them useful traffic information, maybe road geometry data to help them localize themselves or track the lane accurately. There are special traffic scenarios such as lane mergers or work zones. So these are challenging scenarios for autonomous vehicles to navigate safely. Here, a Tesla is driving on a county road, having trouble to localize itself, it fails to track the lane at certain locations, almost having a near crash here. Lane merges are also interesting case scenarios, where here another Tesla failed to identify the lane merge, so it crashed into the barrier. Work zones are also special scenarios. Here, an autonomous vehicle is having a near crash, suddenly changing updating its route. So helping these vehicles in this kind of scenarios is very critical if we want to deploy these vehicles on the roads. And connected vehicle technology can be a great solution, can be very helpful to assist these vehicles. However, the problem is in the almost 97% of the country, we have rural areas, and building this connected infrastructure in these areas is going to be very difficult. Most of the time, we don't have any power or fiber optic infrastructure in these areas, and they are very dispersed settlements. To provide the same level of infrastructure coverage, the infrastructure cost will be very much high. So U.S. Department of Transportation was looking for an alternative way to assist these vehicles, and we came up with an idea of using smart traffic signs, essentially signs that will communicate with these vehicles through machine vision instead of a wireless communication technology. So this is a brief description of how the smart traffic signs are working in the central locations in the dense urban areas. The vehicle will communicate normally with the wireless infrastructure. It will receive the onboard units in these vehicles will receive the messages directly from the roadside units. But in the connecting roads, in the rural arterial roads, we can simply use these smart signs that will relay the same type of information. When the vehicle recognizes this sign, it will activate a preloaded message, in this case, a situational awareness message that contains information about the suboptimal road condition. Here simply tells the vehicle that in this road segment, we reduce the speed because there are road damage, there's locations. And since the vehicle will be able to localize itself with the help of this sign, it can also track the dynamic road users to a higher accuracy. So it can track the pedestrians, cyclists at higher accuracy and predict their position and heading information. So these are some of the applications. We call them V2I, vehicle to infrastructure or infrastructure to vehicle. We are sending a map data message for intersections. If you are in an unsignalized intersections, it's very difficult for CAVs, connected automated vehicles, to identify the road geometry, how the roads are merging in this intersection. Sometimes an autonomous vehicle will fail to see the other side of the road, or the LiDAR technology will not be able to reach the other road segment. In work zones are important case scenarios, and assisting vehicles in the work zones can be critical, especially navigating these vehicles in the detour lane when there's a abrupt road geometry change. We can guide the vehicle on this detour. Similarly, we can provide navigation guidance if you are in a complicated garage parking, and if you are struggling with finding the handicap parking locations or the EV charging stations. If there is one of these signs in front of the garage, it will navigate you to the closest EV charging and handicap parking locations. So not just the rural area applications, we came up with some urban applications as well. Lane merges, abrupt road geometry changes are very important application scenarios. At pedestrian crossings, we can alert the driver, send the vehicle the road geometry data, and send traffic information about that road segment. So our technology uses a machine vision communication. It uses multiple artificial intelligence models. We were able to make a small, affordable device and deploy all these models into this affordable device and made it very efficient to implement this technology. Here, our platform simply recognizes a smart road sign and activates the road geometry information. Normally, this is a very tricky scenario for an autonomous vehicle to understand the lane geometry. So it detects the road users in real time, detects all the roadway objects, traffic lights. It also classifies the road signs. So it receives important information from our smart sign, but it also classifies other normal traffic signs. So it navigates the driver on this detour. This is a very complicated scenario for an autonomous vehicle. It's almost impossible to navigate in this scenario. The system also can collect useful data about the roadway, about the work zones. For example, in this application, is collecting data presence, their real-time position and heading, and sharing this data with the public agencies. So we made the system also useful for cities, counties, their transportation departments, their fleet operation departments. So this was in two-phase R&D project. We are now we almost completed the entire R&D. We are commercializing the technology. In the very beginning of the project, in the phase one, we investigated the technical feasibility, worked on a proof of concept prototype, investigated the potential challenges. But now we came up with more commercial prototype that can be deployed readily to fleet vehicles. It's simply a small onboard device. You put it on your windshield. In the phase one research, feasibility research and testing, we done a lot of tests in different environments, such as under snow. We traveled to a different part of the country, of course, to tested our system. We identified the challenges, even under low light, under bright sun condition, nighttime, even when there is a tree occluding the sign. So it was important for this application to be operating robustly. Even 50% of the sign visibility is lost. The machine vision technology we developed will be able to recognize it safely. So this is an exposure test when there is a bright sun. We lose a lot of visibility, but it's still able to get a safe match. We tested under nighttime conditions when there is complete loss of visibility. The system was still able to identify the road sign. And the last test was here. There was a tree, a branch was covering the sign, a significant portion of the sign, but it still successfully recognized the message ID. we tested the vehicle under different speeds here, under 30 mile, 40 mile, 50 mile per hour. We identified the minimum required dimensions for these signs and did a lot of technical feasibility research. In the phase 2 R&D, we did a lot of prototyping, manufacturing, hardware work, and we tested so many different cameras to get the best result out of our technology. We worked on the design concept of the enclosure and did a lot of prototyping work. And we worked with a manufacturing company who assisted us in this stage. Our university partners also helped us in testing the interoperability with different onboard unit, roadside units. In this technology, what we wanted was we don't need to replace the actual sign when we want to just update the message content. So as soon as when your vehicle enters the range of a wireless communication, it will pull the message updates of the smart signs in the vicinity. So next time the vehicle sees these signs, it will activate the updated roadway information, updated message content. So we worked on signal communication interoperability so that our technology could work with different type of OBUs on roadside units without having any issue. Current experimental work we are doing is kind of one step ahead of our objective. We eventually want to make these signs invisible to the driver, but only visible to our camera system. So we simply make this invisible clear film that you can put on existing traffic sign, and it will simply perform like a connected vehicle layer on top of an existing sign, and it can communicate with our devices. We are also working on how we can use these signs to tackle cyber physical attacks. These are recent concerns that became popular on social media. They call it adversarial attacks, especially traffic sign adversaries are very critical because here, for example, in this application, the traffic sign recognition system in this Toyota vehicle, I guess, failed to identify the fifth speed limit sign here. So what happens is these attackers make very minor modifications on the sign, but it knows the exact position and the shape that will change this classification. So these can jeopardize the safety of connected and autonomous vehicles. Imagine a vehicle traveling for this speed limit sign and an attacker made a very minor modification. The driver will still see anything, but the traffic sign recognition system may identify as 80 speed limit sign suddenly. So instead of stopping on a stop sign, it will accelerate. So what happens is our sign here, it will simply perform like a invisible security patch that will compare the information with our system. So if there is a conflicting information, it will override the adaptive cruise control application. The adaptive cruise control system will be deactivated and it will alert the driver to take control. We are also working, we've been working on a consumer version of the device, not just the business customers, but for consumers. We came up with a nice graphical user interface that you will see maybe in Tesla vehicles dashboard. The vehicle objects or the roadway objects are simply animated in 3D graphics. And the message applications are designed in a way that it will minimize the driver distraction as much as possible. So we did a lot of work in the graphical user interface development. This wasn't an easy phase of the project, definitely. We implemented a lot of ADAS warning applications in our system as well. So in the consumer version of the device, it's not solely going to communicate with the smart traffic signs we have, but it will also be able to support a lot of ADAS warning applications, such as lane departure warning, forward collision warning, red light violation warning, or pedestrian warning applications. Our commercialization strategies was simply to demonstrate this technology to our fleet customers, essentially, who happen to be cities and county fleets who are interested in pilot projects with us. We've been doing a lot of live demonstrations at different exhibition events, Florida Automated Vehicle Summit, Automated Vehicle Symposium, etc. We've been also communicating with the automakers, ADAS manufacturers, and other startups in the industry for possible technology licensing in the future. So we, as I mentioned, we joined Florida Automated Vehicle Summit. We demonstrated the technology on the public road in Miami downtown. What was interesting about it is the high-rise buildings were blocking the GPS signal. So if you were to use your Google Maps, you would fail to go to your destination. And it was interesting because we also had a hard time to go back to our hotel due to loss of GPS signal. Our, however, technology could be very helpful in that scenario since it's using a machine vision localization instead of relying on a GPS signal. So if there is a sign, it's one of the smart sign in a location, maybe in a detour or in a road closure area, as soon as the vehicle recognizes sign, it will update your navigation system and give you the accurate route. We demonstrated our technology on lately in Transportation Research Board meeting, annual board meeting. We demonstrated also Florida Automated Vehicle Summit, as I mentioned. I think this was not Florida Automated Vehicle Summit, but I think another symposium in Tampa. So this was a brief information about ConnectedWise and its technology. We are an Orlando-based startup, but we have a very talented group of people in the company. If you have any questions, feel free to ask. I will also be following the chat box. Feel free to ask your questions also in the chat box. Thank you very much all for joining this speaker session. Hi, Fernando. So let me repeat your question. How will the sign get information in the rural areas? So these smart signs are essentially unique visual identifiers for a preloaded message. It will actually it is interoperable with your existing CAV technology. So if your vehicle is parked to your home location or connected to an authorized network, or when it enters the range of a roadside unit, it will pull the message updates and about all the smart traffic signs in the vicinity. So when you implement a smart traffic sign application, it will receive the messages when it is connected to a wireless infrastructure, but it will simply activate the message when it recognizes through the machine vision system. If we want to change the message after, let's say, in a work zone environment, you want to change the road geometry because your work zone will be changing, you can determine in the message content different scenarios, but at the same time, you can use multiple signs, or you can update the message to a date that when the vehicle is connected to a wireless infrastructure, it will pull the message updates. So if for some reason the vehicle doesn't update any message, it will simply check the timestamp and will not activate a wrong message. So it will make sure that the message is updated. In that case scenario, it will not activate a wrong message. So for rural areas, we don't need to bring any build any infrastructure. We simply put up some of these smart signs in the locations we want to implement. Thank you very much, all. I'll be waiting in the session. If you have any questions, I can answer those, or or I can also go back to the slide and try to explain on the slide if you would like to see anything else. Hi, Brian. You can send an email to this address here I provided in the last slide. Let me also put it on the chat box. You can also add me on LinkedIn by reaching. I think you can click on my LinkedIn icon on my profile.